All right. Go ahead and send me a text for attendance 513-494-6162. Make sure you write logic control in the text and put your first and last name. And I want to get to the PowerPoint in a second, but before we do that, there's a document on your Canvas that looks like this. I kind of want to explain this before we get into the PowerPoint because I want to be able to refer to this and not stop teaching to talk about how this thing is laid out. So when you see the term logical with computers, or computer science, when you see the term logical, it means the same as virtual. And what that means is it exists in memory. It's not a real thing. It's not a real device. It's software. So the way to think about this is these are like rows. First of all, this is an O. That's an O and not a zero. And this is an I. The O here stands for output, and the I's down here stand for input. Okay, and these numbers, you don't really have to worry about these right now, but these are addresses. So basically what you have here is a list of addresses of, we talked about the input-output modules. Well, these are addresses of output modules, and on the bottom you have addresses of input modules. And so the way to think about this, and I'm going to go to the board in just a second, but these numbers here starts right here at 0. Now remember, I mentioned to you that in computer science, when we count, we don't start counting 1, 2, 3, 4. We always start our count with 0. We always start our count with 0. And so what these rows are bit positions. So this is bit position 0. This is bit position 1, bit position 2, bit position 3, 4, all the way up through 7. So basically 0 through 7, that means there are 8 bit positions. But what I want you to do is to think of this like this. Because what that is, it actually represents memory. It represents memory. And we're going to think about memory as just kind of like a Excel spreadsheet row where you have these cells. And so this will be, those numbers represent these cells. So this will be cell 0, 1, 2, 3, 4, 5, 6, all the way out to 7. So that's one row of the table that I just showed you. And it was for the top one was the output module. And what you can do in these cells is these cells can store information. And since we're talking about digital information, a cell can store a 0 or 1. I'm going to come back to that in a second because that's not true in all cases. But with PLCs, I can put a 1 or a 0 in any of these cells. So all this table is showing you is the different bit positions in this, what they call this is an image table. So you have two image tables. You have an output image table and an input image table. And what an image table is basically an image of the input module terminal connections and an image of the output module terminal connections. So I'll show that when we get into the PowerPoint. But so think of this as just a grid. So this whole thing right here is just like a grid, like in a spreadsheet. Just think of it as a grid like this. I'm trying to draw the best I can. So it's a grid. And so this, this 7 right here, that's just the bit position of that last cell, maybe right here, if that makes sense. So this will make a little more sense when I get to the PowerPoint because I have a nice slide I want to show you that kind of shows what's going on. So basically what this grid system does is it just stores zeros and ones in certain locations in memory, and it's kind of a mirror image of the I/O section of the PLC. Okay, so just keep that in the back of your mind. We'll come back to that in a second. Let me get to the PowerPoint that I think we ran out of time. We were talking about the CPU, and we know CPU is a central processing unit. We talked about the fact that an actual CPU is composed of 3 main parts: a microprocessor, memory, and a power supply, some type of power. We mentioned the fact that in this class, we're going to treat the CPU, at least after this discussion, we'll treat the CPU and the microprocessor as kind of one and the same device, even though we realize the CPU contains a microprocessor. CPU is more than a microprocessor. We talked about this memory. So memory is where we basically store our program temporarily. There's a difference between memory and storage. Storage is where we store our program long term. We'll talk about types of memory here in a second. And then I wanted to move to this slide. Now this slide is actually pretty important. So I asked you to print your PowerPoints out as note pages, or maybe you're taking notes. You want to mark this slide and make sure you're familiar with some terms on this slide. Now, some of them you're already familiar with, like the term bit. A bit is short for binary digit, and you know a bit can be a 0 or a bit can be a 1. So a bit is just a single binary digit. A byte is a unit of bit. It's a certain number of bits. A byte is equal to 8 bits. A byte is equal to 8 bits. Now, earlier we talked about the differences and the similarities between PLCs and PCs. And pretty much they're the same device. A PLC is a computer. But there are some differences, and here's one. I want to point out one big difference between a PC and a PLC. PCs, and this includes like your cell phone, microprocessors, everything else except for a PLC. PCs are byte-oriented devices. Byte-oriented devices. A PLC is a bit-oriented device. A bit-oriented device. So if I can go to the whiteboard for just a second. You know that, well, now you know that anything that goes inside of a digital device has got to be in the form of zeros and ones. So how are those zeros or ones partitioned? How are they stored? Well, the smallest, let's say you were in your Word document and you typed my name, you type R-O-N, you type Ron. Well, you can't put an R, you can't put a O, and you can't put an N directly in the memory, because everything is represented as zeros or ones. So I don't know off the top of my head what R is, but R would be represented as a series of bits. It would be 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. And that would represent the R. The O would be represented as another series of bits. It will be 8 of those. Each one of these letters will be represented as a series of bits. And if you were to open up memory, let's say you can see inside of your digital device, the smallest chunk of information you can access is 8 bits, which is called a byte. So most digital devices are byte oriented, which means the smallest chunk of information you can actually access, we say it's atomic. Smallest atomic piece of information you can access is a byte, 8 bits. PLCs, you can actually access individual bits. That's a huge difference between a regular PC or digital device and a PLC. And that kind of, the fact that PLCs are bit oriented is one reason they can do what they do. And this will make more sense as we proceed through the slide. Now guys, at any point, if you have any questions, just interrupt me, because this is some cool stuff, but if you're not used to it, if you haven't heard of it, it might be a little bit confusing. All right, so let me go back to where we were. Oh, not there. You want to know these terms. So you want to know a bit is a binary digit. A byte is 8 bits. A kilobyte. Now, first of all, you want to be careful. This can get really confusing. Let me go back to the board. So, you know, you guys are engineering students. And so when you think kilo, you think 1,000. But in the binary number system, kilo is not 1,000. Kilo is equal to 1024. And the reason it's equal to 1024 is because we don't deal with base 10 numbers. We deal with base 2 numbers with digital devices. We deal with the binary number system instead of the decimal number system. So in the decimal number system, when we think of kilo, we think of 1,000. But computers deal with not decimal numbers. They deal with binary numbers. And 1,000 is equal to 1024. Now, next week, we talk about number systems, and that'll make a whole lot more sense. But for now, a kilo is 1024, 1024. But then you're going to have a K with a capital B. You're going to have a K with a lowercase b. Okay, so this one, uppercase b. This is the one that most of the time this is when we talk about KB, we're talking about the big B. But this top one is kilo bytes. And the bottom one here is kilobits. Now, I don't want to confuse you, but I'll just tell you a little bit of historical, some historical information. A long, long time ago, I'm talking like, I don't know, this was pre-web. You know, this is pre-web, not pre-internet, pre-web. I don't know. So what's the difference between the internet and the World Wide Web? Somebody answer that. What is the difference between the internet and the World Wide Web, or is there a difference? Going kind of off topic here, but are they the same thing? If I want to get on the internet, I want to get on the World Wide Web. Am I talking about the same thing, or are they something different?
The internet's the hardware, and the World Wide Web is the software.
That's exactly right. The internet is the hardware. The internet is a network of networks. It's a bunch of networks connected together. So it consists of hardware like fiber cable, copper cable, routers, switches, a whole bunch of hardware that you may or may not have heard of. That makes up the internet. So it's much like a computer can have computer hardware, the hard drive, the screen, the mouse, and then you put software on it. Well, that's the way the internet is. You got the internet, which is this is basically hardware, but on the internet you can put software, and one piece of software is when you type www, that's the World Wide Web. But that's not the only software on the internet. There's also FTP. That's file transfer protocol. That's another part of software that can run on the internet. There's also email that uses another protocol. So the internet actually came long before the World Wide Web. This internet thing was a product of the 70s, late 60s, early 70s. It was an agreement or a research project between the United States military and one of the colleges out west, I believe. And so that was around the 60s or 70s. The World Wide Web came in the 90s. That was a British thing. It was a British dude. I forget his name. But the point I'm making is none of this was here on the internet. The internet was just a network of networks, and you had to communicate back and forth between computers. None of it was with the graphical stuff that you're used to. When you got on the internet back in the day, it just came up, and there was a cursor on the black screen blinking. And when you want to move information around, you couldn't talk. There was no camera. There was none of this stuff you have right now. You had to actually type this information out. And I can actually send through the internet a letter or a document from one point to another. But when you sent it out, you had to connect it to something called a modem. You actually transmitted. There was no fiber cable ran. There was none of that stuff. You actually transmitted bits through the telephone line. I know you guys are probably, what do you mean telephone line? Well, cell phones weren't around forever. Right now, you talk on a radio wave when you talk on your cell phone. But back in the day, there was none of that. Everything was through copper, a copper cable. So it was a telephone wires everywhere. And you would send information back and forth across the telephone wires, but the modem would send it bit by bit. So you'd have, remember when a second ago I said you had the letter R? You had 8 bits to represent the letter R. Well, each one of these bits, this is the serial data transfer that we talked about. Serial data transfer, where you send this bit by bit by bit by bit. So you probably can't even find a modem now. Maybe there's a museum somewhere you might see a modem. But back in the day, they would rate the speed of modems in kilobits. And it gets confusing because back in the day, a kilo was 1,000. The speed would be kilobits per second. And this was 1,000 bits per second. It wasn't even that 1024. Now I think I got on Google and I look and they say, it gets confusing. So I don't want to confuse you. So back in the day, it was kilobytes would be 1,000 bytes. I'm sorry, I said that wrong. Kilobits would be 1,000 bits. Kilobyte would be 1024. So I don't want you to be confused. In this class, we'll deal with the big K and the lowercase b. But so kilo for us is going to be 1024, not 1,000. So at some point, you'll have to calculate how many actual bits you can put in those memory cells. And you just got to remember that 1,000 is this number, or a kilo is this number right here, and not 1,000. And I'll point that out when I get to it on the slide. And if you have questions, just ask me. Okay, this is why I run out of time, because I get sidetracked with this other stuff that I want to tell you about. But everything's interesting. God made everything so interesting. Okay, where were we? So I was asking you to make sure you, where is that slide? This one. Okay, so going through this slide again. So a bit is a binary digit. A byte is 8 bits, and a kilobyte is 1,024. So it'll be 1,024 bytes. And each byte can be, well, we'll get to that. So just know the difference between the lowercase b and the uppercase b. And the most important one for us is this. That's kilobytes. Now this one right here, a word. Again, these are all sizes of memory. So we can have a bit, which is a single space for a 1 or a 0, single 1 or 0. We're going to have a byte, which is a group of bits. It's going to be 8. A byte is always 8 bits. And then there's this thing called a word. Now, a word is machine dependent. You want to write that down. Words are machine dependent. And what does that mean? A word is machine dependent. It means whoever designs the device, they can make the word size whatever they want. A word is machine dependent. The manufacturer can make the word size wherever they want. They can have a word that's one byte long. Remember, a byte is 8 bits. They can have a word size that's 2 bytes long, so it'll be 16 bits. They can have a word that's 4 bytes or 4 bits, 4 bits wide. Actually, that's another unit. I don't have it on the slide, but a byte is 8 bits. 4 bits is called a nibble, a half a byte, a nibble, like you might nibble on something. So even though a word is machine dependent, for us in this class, a word is going to be equivalent to 16 bits. And I'm going to explain that in just a few minutes. So let me go back, because on the quiz, I want to be clear. I want everybody to know what I'm saying. If I ask you to define a bit, you're going to tell me that's a single binary digit, a 1 or a 0. If I ask you to find a byte, you're going to tell me that's 8 bits. If I ask you, well, kilo means what? Kilobyte. Well, that's going to be 1,024 bytes. If I ask, well, how big can a word be? Well, a word just depends. A word is machine. Yeah. A word is, that's a bad joke, by the way. A word is machine dependent. A word, it just depends on the manufacturer of the machine. For us in this class, a word is going to be 16 bits. So a word is going to be 2 bytes. And I'll show you why in a minute. Let me go back to that diagram. And this will make a little more sense now. So remember when I told you about this chart, and let me erase these lines. And these charts just kind of model a grid, and these are the Like basically what over here, these are the addresses of the grid. So this is row 0, this is row 1, this is row 2. So I can have a grid like an Excel spreadsheet. I can have a grid. I'm trying to draw with my mouse. It's terrible. And so I can say output colon 01, and that would be this row right here. Bit position 6, and that would be this bit position. So I can actually look inside of there and see what's in there, a 0 or a 1 in that bit position, anywhere in this entire grid, And the other thing I want to point out is that look at how this is numbered. It starts out with 0, and then it counts 0 through 7, and then it stops. It doesn't go 0 through 7, then 8, 9. It skips over 8, 9, and starts right here at 10. So this, even though I have the space here, this is really just one big thing all together. The space is just there. The space is just there for convenience. But look at how these cells are numbered. They're numbered 0 through 7, and then 10 through 17. So down here, if you look really close, that's kind of small. So if you zoom in on that, it says, note, the above input-output addresses are for Allen Bradley PLCs and are in the octal numbering system. So the software we're going to use at Logic Pro software mimics Allen Bradley, a particular type of Allen Bradley PLC. And Allen Bradley PLCs, some of them use a different numbering system. Well, most PLCs use a different numbering system than base 10. They actually use a base 8 numbering system, which is called octal. Now, next week, we'll talk about numbering systems, and you'll understand that. So don't worry about it right now. But just know that each one of these numbers in this rectangle represents a memory cell. And if you tell me which row and which cell number, I can go right to that particular cell and look to see what's inside of it. And inside of it will be a 0 or 1. And the other thing to know is that when you count, you'll see that there's 0 through 7, that's 8, and then 10 through the 17 is another 8. 16, there's 16 cells, 16 locations in this block of memory, 16 of them. And that's why I said for us in here, a word is going to be 16 bits. This will be one word of memory. One word of memory. Okay, go back to the PowerPoints, and then you can ask me questions if you want. So this slide right here, make sure you you put a note on it, a mark it, a star, or whatever you're doing to identify it. And then I already mentioned the fact that each memory location has a unique address. So I can actually go right to that particular 0 or 1 stored in that grid system I showed you about. And this is only true for PLCs. This is not true for PCs and other devices. Remember, and most other devices, the smallest chunk of digital information you can go to is a byte, which is 8 bits. So if you go to that address, you're going to see 8 zeros and ones. That's the smallest chunk you can access. But in the PLC, you can actually go to a particular bit position and examine that bit position. And that's what makes PLCs so powerful, and you'll see why. This kind of speaks to, it says one location per coil or contact. What this means is that in that instructions that I showed you, like when we talked about input, outputs being represented by switches, and we represent actually inputs being represented by switches or buttons, and outputs by, well, we use a lamp, but we can use any kind of output we want. But let's say I have a button, and you know a button can be open or closed, right? You know that. So that button can be open or closed, and that lends itself really, really well to a binary number system. When something can be in one state or another, it lends itself to binary. If something is in one state, we can say that state is a 1. If it's in the opposite state, we can say it's a 0. And so we can say a switch that's closed, we're going to give that a binary value of 1. A switch that's open, we're going to give that a binary value of 0. So now I can mimic the state of a switch in software by just looking at the presence or absence of a 0 or 1. This is the power of the PLC. And so what this point is saying is each instruction, each input instruction or each output instruction is represented by a single bit. And I'll show you that here in just a couple slides, actually in about 2 slides. And then the other important thing on this slide is this. So memory terms, volatile and non-volatile. You want to know what that means. Volatile and non-volatile. So before I talk about those 2 terms, let me tell you about the 2 main types of memory. So in the computer world, there is random access memory, and then there is read only memory. And normally they don't write it out. They'll call this type of memory RAM. If you ever seen that when you buy a computer or some digital device, they'll talk about the RAM. And down here they call this ROM. So random access memory, read-only memory. And what you want to remember is that RAM is volatile, ROM is non-volatile. RAM is volatile, ROM is non-volatile. Volatile memory, what it means is that if you remove power from it, if you take away the power, then the contents of the memory disappears. Whereas RAM, I don't know if I said that right. RAM, I have to go back and watch my video. I might have to edit that. RAM is volatile, which means that if you remove power from it, whatever's in RAM, it's going to disappear. ROM is non-volatile, so whatever contents is in there, whether it's power connected or not, it's going to always hold those zeros and ones. What does it mean, random access? Anybody knows what that means? What does it mean, random access? You ever thought about that? Normally when they draw memory, they'll draw it like these cells. I always think of memories as cells. So let's say I got bits and bytes in here. So I got maybe a code in here. I got something like that in there. Well, a long time ago, at the beginning of the electronic computer revolution, all memory was sequential access, which meant that, let's say I wanted to grab this piece of digital information right there. I would have to go in here and look bit by bit by bit and actually get to that and then pull it out of memory. Whereas random access memory, I can access any location in memory in equal times. So I'll just tell you now, all memory is random access, even if you don't, ROM is random access. So they don't make sequential memory anymore that I'm aware of. This is like the horse and buggy. But you do want to remember that RAM is volatile, ROM is non-volatile. Volatile has to have power connected to maintain the contents of the memory. ROM is non-volatile. You can remove power. And typically, hold on a second, my light went out. Motion detector, I got to adjust it over to me. It's adjusted on the tables in this classroom where I am. And since there's no students here and no motion, the lights keep going out. I forgot what I was going to say now. Yeah, I had a point and I lost it. The lights kind of got me off track here, but I guess maybe it'll come back. Okay, let me go back to the PowerPoint. And, oh, I know what I was going to say. So the reason why do we need ROM? Anybody know why we need ROM in digital devices? Why do we need ROM?
Because you gotta store data for power outages, like your hard drive.
Yeah. So a PLC with no software in it is basically like it's a piece of garbage. You can't do anything. You just got stuff. What really makes a PLC or a computer or your cell phone, what really makes it come alive, now the value is the software. The software is what makes the device a device. Well, when you turn everything off, a PC, when you turn it off, the hardware stores the main part of the, well, not the main part, a big part of the software is the operating system. We discussed that. Well, when you turn it off, the machine doesn't know anything. It's got to have enough knowledge, and it's got to have the basic programs to tell it how to boot up and to put certain things in place just to get ready for you to use it. So you gotta have that stored somewhere permanently that doesn't need power. So that's like a starting point. So you're gonna have ROM in any kind of computing device. You gotta have a small amount of ROM. This you may or may not need, but this you gotta have. This is more like a scratch pad. When you want to work on something, it's in RAM. It always exists in RAM. If you want to keep it, then you move it over to long-term storage like a thumb drive or hard drive. You can read and write to this. You can only read from this, and hence the term read only. You can't write to it. So you can read to this and you can write to RAM, but you can only read from ROM. So anyway, that's only important if you're going to buy some of this hardware we're talking about, but it's still good to know it. All right, I'm getting off track here. So let me go back to, okay, so we're talking about this. Now, anybody have any questions on this particular slide right here? You'll see this again on your quiz or exam or somewhere. Anybody have any questions or comments on any concept, point, term, anything on this sheet? Okay, now, here is how, this next slide is how I want you to think about memory. I want you to think about memory like this. Think about memory as having these three areas. Think about memory as having, even though we know that technically this is different. This is like the hard drive, and this part over here might be like RAM. We're gonna just say that anytime I can store something, I'm putting it in memory, all right? Whether it's the hard drive or RAM, it doesn't matter. We're gonna call it all memory. And not only that, we're gonna say this memory is divided into sections. This would be the long-term storage part of it. So that's when you save a program. But over here, this is the RAM part of it, the short-term part of it. And these tables, this table right here and this table right here, what that is that document I showed you with all those cells on it. The one on the top of that document was called, remember those addresses started with O's, and the one on the bottom, the addresses started with I's. So the one on the top was called a output image table, and the one on the bottom are called input image table. Now in the actual PLCs, I know some of you actually do this for a living. You may or may not have heard the term image table. In textbooks, they call it the image table. In the real world, they'll call it a data table. Most PLCs I've looked at, there'll be a way to access the data table. And so what this is an image of, I like the word image because, I mean, both terms are correct, data table or image table. What is it an image of? It's an image of the output modules, or it's an image of the input module terminal positions. And so what I'm saying is, if you think about the input module like this, now this right here, everything on the left side of this slide, that's hardware, and everything on the right side of this slide is software. So this input image table, remember that exists in the memory. This is memory. And so this input module, what you have here, is not shown in this drawing, but you have these screw terminals we talked about. There's a screw terminal here, there's a screw terminal here, screw terminal here. There's all the way down, and it doesn't show it in this picture, but there's 16 of them for the PLC we're going to use. There's 16 of these screw terminals that you can connect buttons or switches to. And so I have a button here connected to this terminal and a switch connected to this terminal. And what I'm trying to show you here in this slide is each one of these physical bit positions on this input module map directly to a bit position in that grid that I told you about called the input image table. Each terminal maps directly to a bit position, a cell, like an Excel spreadsheet. And that cell, since it's digital, can only store a 0 or 1. And what that 0 or 1 means in this case is the state of a switch being open or closed. So if you examine this closely, look at it closely, if you zoom in on it, you'll see that right here, I have this button, and the button is closed. And it's connected to this screw terminal that I'm not showing you. Well, what this blue line is showing you is that maps in memory to a location in that input image table. And it's storing a 1, and the reason it's storing a 1 is because that switch, that button right there is closed. If you were to press this normally closed button and open it up, then this would change to a 0. So just by looking at memory, let's say I couldn't see what was outside of memory. I can only see the bit positions in memory. Just by looking at whether I have a 1 or a 0 right there, I can tell if this button connected, mapped to this, is open or closed by just looking at the bit position. And it's the same thing with the bottom switch. If you look at that, I have an input over here, it's open. So this maps to this bit position right there. And since this is open, this image table is going to store a 0. So in software, we can tell if a button or switch is open or closed by looking at the presence or absence of a 0. But if it's a 1, we have an input that's closed. If it's a 0, we have an input that's open. And this is the way the PLC determines if whatever's connected to that terminal is open or closed. By looking at the image table, it can tell if a device is in one state or another. So that is important. And it is the same with the output. So this now have the output module. There was 2 image tables or 2 data tables. There was an output image table and there was an input image table. Well, now we're talking about the output. So what happens is, depending on what's in the output image table, when the PLC runs, it's going to either turn something on or off. Let me say that a second time. Depending on the state of the bits, in particular bit locations of the output image table, the PLC is going to turn devices on or off. And so, if you look at the slide, like right here, in this bit position, there's a 0. So whatever is mapped to this, and the way you map this terminal to that bit position is by something called the address. This bit position is actually mapped, or I should say this screw terminal is mapped to this bit position. So when the PLC scans it and sees a 0, if this is on, it's going to turn it off because there's a 0 right here mapped to it. This one right here is a 1. So whatever's mapped to this bit position in the output image table, whichever screw terminal is mapped to it, when the PLC scans it and sees that this is a 1, it's going to turn this output on. So all the PLC sees, it doesn't know anything about open and close. It only sees 0s and 1s. It's looking at memory. Okay, so that's the end of this. Now, does anybody have any? We went through a lot. This is a short slide presentation, but there's a lot of good information in there to understand how PLCs work. Anybody have any questions or comments on this? I got enough time to go to that other one. I'll probably run out of time, but before I do, I want to make sure we're cool on this stuff. Anybody have any questions on anything in this particular PowerPoint that might be not clear, confusing? I mean, you want to make sure that this one you mark, you want to know the pieces of memory for this also, you know, for everything to make sense. And these 2 explanations I just gave, if you follow that, I think the next PowerPoint is going to use this again to make it even clearer. But if you follow that, then you're in a good position for us to move on. Any questions or comments on this particular PowerPoint?
Do PLCs have raw power input to power all the outputs?
Oh, okay. That we get into that in this next PowerPoint. So let me go to that. That's actually a good question. Let me go to the next PowerPoint, and we'll talk about that a little bit. Okay, so now remember what we're doing is we're talking about we kind of gave you an overview. I showed you a picture of a PLC because I'm not in front of you. I couldn't bring the actual PLC in to point to it, so I showed you a picture. We identified some major parts of the PLC, the input modules, output modules, call it the I/O section. There was a CPU as an important section. Power supply is an important section. There's a communication module. There was different parts that we pointed out on that modular PLC that I showed you. And then we started to drill down into some of the parts individually. So we just got through talking about the CPU part of it. So that was that big module in that picture. The one on the left, that was the CPU module. The furthest one on the left was the power supply. And somebody asked a question about power, so we'll get into it here. Let me see, make sure it is. Yep, okay, we'll get into it here. All right. So the title of this is Discrete versus Analog I/O. And most of the time, you guys will be dealing with discrete I/O. Now, you know the difference. Well, you know what analog is. That means continuous. So what is discrete? What do we mean by discrete? Well, we'll get into that. Basically, if it's discrete, that means that the device can be in one state or another. Discrete means that the device we're considering can be in one state or another. The device we're considering might be a switch. A switch can be open or closed. The device we are considering might be a button. A button can be open or closed. The device we're considering might be a motor. A motor could be running or not running. A light bulb can be on or off. Anything that you can think of that can be described as being in one state or another, not a set of continuous states, but one state or another, that's what we mean by discrete. And most of the time when you're dealing with these PLCs, you're going to be using a discrete I/O, discrete. Not all the time, but most of the time, by far, it will be discrete. And so this term right here, bit-oriented, you want to mark that. That's really, 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 really important. Bit-oriented. And that means that those inputs actually address an individual bit. And I've already showed you that in the input image table, in the output image table. When you had a switch or button, it was mapped directly to a single bit. And if that button was open, that bit was a 0. If you close that button, then that bit got changed to a 1. It's bit oriented. So the main difference between a PLC and a regular computer is that PLCs are bit oriented, PCs are byte oriented. The smallest piece of information you can access in a regular PC is a byte. The smallest piece of digital information you can access in a PLC is a single bit. That's important. Know what the term bit-oriented means. So we're going to talk about the input module. What does the input module do? Well, here's a couple, does a lot more than this, but here's the main points to think about when we talk about the input module. So we have the most important thing it has to do is tell if a button is open or closed, or if there's a signal or no signal from the input device. So that's the main thing we want to know. Is this switch open or closed? So it's going to sense when a signal is received from the sensor, but really I probably should have said switch here or button, but it could be a sensor. We have to convert the signal to the correct voltage for the PLC. And somebody asked about power. Well, okay, well there's a couple ways we can connect that. I want to show you that here hopefully in just a second. And the other thing we have to do is isolate the PLC from voltage fluctuations. We call that filtering. Most electrical devices have some means to hold the voltage steady. And then identify to the processor which sensor originated the signal. I mean, which button or switch did the signal come from? Well, we deal with that through something called addressing. We'll talk about that. Every device in the field, anything hooked to that PLC, will have a unique address, and the PLC can look at that address and tell where signals come from or where they need to go to. Now I want you to mark this next slide. This refers to output modules. There are 3 types of output module classifications. You can have an output module classification transistor, output module classification of triac, output module classification of relay. Now you already know what a relay is, so I'm not really going to say a whole lot about that. But what is a transistor and what is a triac? Well, a transistor, both the transistor and the triac, they are solid state devices. Now I asked you a couple days ago to remember what the term solid state means. And just in the simplest sense of the term, it means no moving parts. It's electrical devices. They don't have moving parts. They're based on a piece of silicon, a silicon crystal. You probably call it an IC chip. Well, a transistor is not an IC chip. IC chips are built from transistors. So it's the smallest piece of electrical device you can have that's solid state, if I can say it like that. The thing to remember, though, is that transistors can only control DC devices. The triac can only control AC devices. So if you were to go buy PLC, you have to figure out a couple things. First, how big or small does it need to be? That's going to be determined by what you need to do with it. I mean, if it's going to control a garage door, I mean, you don't really need a whole bunch of functionality there. You can deal with just a small PLC you can hold in your hand, fixed I/O. You don't need modules. If you're controlling the whole factory, you're going to need something else. You also have to determine, well, how's this thing powered? Somebody mentioned power a few minutes ago. It depends on the devices you use. Are we using DC power or are we using AC power? The things that we want to power with the PLC. And if it's DC, then when you buy the output module, if it's a modular PC or when you buy the fixed I/O, you got to make sure that you have a transistor output. It's going to use transistors to control the thing that you hook to the output. Whereas the triac is going to use a triac, which is, again, a solid state device that controls AC devices. If it's relay output, it doesn't matter. A relay can switch AC or DC. So you want to remember this slide, triac, transistor, relay. And what I'll probably ask on the quiz is, what kind of device can this particular classification, what kind of device can it control? You'll say, well, transistors can control only DC. A triac can control AC, only AC. But the relay can control either AC or DC devices. Now, somebody asked about power. Let me go up to the camera. I'm probably going to run out of time here, and I'll have to pick on this on Friday. So power in the PLC, and it just depends. So in general, in electricity, we have something called a source or a sink. Think of plumbing. Think of a sink. If you're going to sink current, something's going down the drain. If you're going to source current, something's coming out of the faucet. So let's say I have that output module. Here's my output module. And here's a connection to it. And the thing that I want to control is over here. So let's say, I don't know what it is. We're going to say let's just say it's a light. It's a lamp. So this is a lamp. On some PLCs, to get this to work, what you have to do is you actually have to take and connect this to power. So this would be my power, my plus, and then you take this and you would connect it to the screw terminal, and this is the output module. And so whatever somebody asks about power connections, if I have 4 terminals here, and I have 4 things hooked to that terminal, each one will get its own power. And if you look at now this is important. I'm going to run out of time, but just stick with me. If I connect this to power, then this has to be ground over here. And that means current is going to come from power into that screw terminal. We say that this is sinking power. So this would be a sink. Well, maybe I get another PLC that doesn't connect up like that. Again, this is the output module. And here's the screw terminal. Maybe on this particular brand of PLC, I have this same device, the light bulb, but I connect it up. And this is connected to ground. This is now my positive and this is my negative. And so we call this a source. This thing is going to put out current or source current. So current is actually going to come from the PLC to light the light bulb up. And it'll put out each one of those screw terminals would have its own source of power to source current to each device that we have connected to it. So if you're buying a PLC, and I'm right here out of time, you got a lot to consider. How big does it need to be? What do I have to control? Is it discrete or is it analog? Am I going to source current or sink current? It all depends on what you're doing and what you connected up. The hardware part of this is a whole different story than the software, which is really what we're gonna get into here. We used to get into the hardware back when we were over on Victory Parkway, but once they combined the College of Applied Science and Engineering, we gained some stuff, but we lost a whole lot of good stuff. Those were the good old days. Okay, guys, I'm gonna run out of time. I'm done, but let me just say that I'm gonna finish this because there's some other information here that we kind of get into analog. The other part is, well, how does discrete and analog differ? And so we'll get into that in the next slide. Now I know you guys have to go, so I'm gonna end this here, but I will stick around in case anybody has questions. I don't have another class. I'm taking an accounting class, and boy, I mean, I've had physics, I've had nuclear physics, atomic, I have all kind of smart people stuff, and this accounting is kicking my behind. It's a whole different thing. But anyway, I'll stick around. You guys have a good day. Stay warm. If you have questions, I'll stick around for the people that have questions. And other than that, I'll see you on Friday. Now, we're going to go through the rest of the week, or actually just Friday, through the video. And I got up to the level of the dean as far as approving this online thing. I don't know what's going to happen after that. They haven't denied or approved anything. They just kind of extended it for the week. So I'll keep you updated, and we'll see how we're going to go on that. Have a great rest of the day, guys. I will see you on Friday. And if anybody has any questions or comments, I'll stick around. I won't turn off the camera until you guys have signed off. Thank you, and have a good day. I know, Kyle, yeah. Accounting does suck. Bradley, are you there? You have a question, or are you just
Yeah, I sent you a message before class regarding my accommodations for the quizzes and exams.
Oh, okay. How did you send it? Did you text me? Did you email me? How did you send it?
So I sent you an email. I forget. I can look when it was
Really?
the first week.
Oh, I'm sorry. I didn't. You must have sent it. Did you send it to my UC email?
So I
I don't
sent it.
remember.
I sent it to your personal one, and then I copied you on your UC one.
Okay.
I
I'm sorry.
can.
I didn't. I don't know why. I don't know why I didn't see that. Okay.
You're all good. Yeah.
I'll take a look at that email, and then I'll respond to it. It probably won't be
Okay.
until later on, but I'll
Yeah.
make sure that I take a look at that before the next quiz.
Okay. Yeah. I was just trying to figure out. I know that most of the quizzes are in the setup of just doing them on Canvas. So I was just trying to figure out the best way to, because I have the extended time on them. So just trying to figure that
You
out.
know what I could, there's a way, I've done this before. There's a way for me to, I gotta go back and figure it out again. But there's a way for me there's a way for me to do that where I can extend the time on just your quiz. There's a way for me to do that. I gotta figure it out. I can't remember. I did it like 2 years ago, or whenever we started using the Canvas thing. But I'll figure that out, and
Yep.
then we'll work it out.
Sounds good.
Hey, thank you for making me aware of that. I'm sorry I missed
Yeah.
your email.
No, you're all good. I just wanted to make sure that my email was going through, and I think I tried to text it, so I don't know if.
Okay,
But
I'll check that
we'll
out.
figure it out. Yep.
How about the other quizzes? Did you do okay on the other quiz?
Yeah, I
The
got
one-
a 9 out of 10. I think it was
Okay.
the single or serial. It was the one calculation.
Okay.
But I think I just did it by 8 bits, so I didn't multiply it right. So
Oh, okay. Okay. Well, at least you know what you did. So we'll probably repeat that on the exam, so you'll know how to do it for the
okay.
exam.
Yep.
But yeah, thank you, and I'll make sure I'll take a look at that email. I appreciate it. You have a great day, man.
You too. Thank you.
Thank you.